Hi there, lesson number 2 on spectra. We're going to continue with our idea of this absorption spectra, where energy is absorbed by electrons when incoming photons hit them. Okay, so in this diagram, we have got some energy levels of a simple atom. I need you to copy this down right now. We've got our energy levels E0, E1, E2, and E3. And remember, as we go up, they get closer together. The numbers, which you should be able to see, and I'll need you to copy these down. Use some lines on your line paper. These numbers, 21.8, I'll do this big, but then you can write them small. Each of them is times 10 to the negative 19. So this bottom one is 21.8. This one, 5.42. This one, 2.42. And the top one is 1.36. Each of these has a negative sign in front of it because you're going down the levels, although the numbering system works up the way. Make sure you can copy this down. Don't write the numbers here. Put the numbers over to the side. Each one of these numbers is followed by times 10 to the negative 19 joules. Okay, I've written that. Whether that's any better in green this time, I don't know. But make sure you copy all these down. So pause the video if you need to, and make sure you get these energy numbers for each of the levels copied down. We're going to do some sums with these. Okay, we're just going to rub this out whilst you're copying those down. If you've paused the video and get the numbers, I'm just going to rub out all the green stuff and put back in the energy levels. Okay, now the first question here is going to be this. I'm going to take this off just for now, but I'm going to write down the question, part A. Okay, the first question is how many possible energy transitions, I'll put possible twice. How many possible energy transitions are there? If you've put possible twice, it doesn't matter. You're the only person who's going to see it. How many possible energy transitions are there from level E0 to E3? So I'm going to write the questions here. I'm going to do some calculations in a minute, but let's go back to this and let's start over at E0. We want to go from E0, it says, to E3. There's E0, there's E3. How many possible transitions are there? Now, a transition is just how many possible steps is it possible to make to go from there to get you to there, and how does it work? Well, let's do it like this. 1, 2, 3. Okay, that's the first 3. We did this last lesson. What other transitions are possible? Well, if you do this first one, it's then possible to do that one, and then it's possible to go from there to there, and lastly we can go from there to there, and those are all the possible energy transitions. 1, 2, 3, 4, 5, 6. There are no other ways of getting there from E to naught, and 6 of them is what you've got. You can mark them on. If you've got an exam paper, for instance, you can mark them on the question. It's not a problem. And then you can just say that there are 6 possible transitions that we've got. Six. So the answer is 6. There you go. Right. Now, let's have a look at question B. What is the largest amount of energy that can be absorbed and what we're going to do here is we're going to look for the biggest arrow, the largest arrow, the biggest possible jump, and the biggest jump is from E0 to E3. E0 to E3. Now I ought to say here that if you write this in the exam, you're not going to get any marks because that could be interpreted as being a minus sign. So you really need to say something sensible like 2, or I think you can get away with this. Okay, or you could say between E0 and E3, but don't do that with a minus sign. And certainly don't say the other way round. Don't say from E3 to E0. This is energy being taken in to allow you to get up higher. If you go from E3 to E0, that's not absorption, that's emission, and that's a separate thing altogether that we haven't covered yet because we're still doing this thing called absorption, is taking in some energy. So that's acceptable, that's acceptable, that's acceptable, that isn't, and E3 to E0 is not acceptable. Okay, so be careful when you're answering these questions. So I'm just going to leave that one, E0 to E3. Right. Now, second bit of this question is how much energy is needed for this transition. So you've just got to take the numbers off here. We know it's E0 to E3, and we're going from 21.8 to 1.36. Okay, just ignore the negative signs. Negative signs just show the floors that you go down. Okay, numbers go up, floors go down. So I've got 21.8, which is the bottom one. Take away 1.36, and that is all multiplied by 10 to the negative 19 joules. And then I can work that out on my calculator. Here we go. You can follow me as well. 21.8 minus 1.36 equals, and that is equal to 20.44 times 10 to the negative 19 joules. Now, this isn't a final answer going on here, and you can see that we've got some decimal place issues because we've got 1 decimal place here, but we've got 2. By the time you combine them together, you're going to have 2 decimal places. Don't start rounding this up at the moment to 3 significant figures, because we're going to do something else with this number. So how much energy is needed for this transition? The answer is you need 20.44. So if you have got exactly, if there's an incoming photon that carries exactly 20.44 times 10 to the negative 19 joules, then the electron will go from there to there in one jump. What happens if it's slightly less, 20.43? It's not going to do it. It's not interested in doing it unless it's the exact amount of energy, because 20.43 would leave it just below the floor here, and you can't get out at a floor there. You've got to be at exactly the right floor. What about 20.45? Well, that's too much, and that would take you above the floor there, and you can't get out above the floor. Don't tell me, yeah, the lift stops 2 foot up in the air, you can jump down. This is where the analogies don't always work. Okay, you need exactly the amount of energy that photons are carrying, or you can't do it. Now, and you're going to say, well, what's the chance of that happening? Well, photons, there's an absolutely huge number of photons that are flying around. They're coming out of the sun, and they're going to have a huge range. I mean, it's almost an infinite number of photons. It's not quite an infinite number, but it's an extremely large number of photons that are leaving the sun, and every single one of them will carry a different type of energy, a different amount, and they're all going to be streaming along. They're all going to be hitting the Earth, and they could excite. There could be just one or two. Now, you only need one photon. You only need one photon carrying that amount of energy to give the electron enough energy that it is absorbing to go and do that. All the others are just going to stream past this atom and are just going to disappear, okay? But there will be, in all the billions of photons that are streaming out of the sun, there is going to be one, because you only need one photon to move one electron. Okay, next bit. I'm just going to write down that number because I'm going to use that number again. You don't need to do this again, but it's 20.44 times 10 to the negative 19 joules. Okay. So I'm just going to transfer that back here. 20.44 times 10 to the negative 19 joules. So here's a photon, and it has got exactly that amount of energy which is absorbed by the electron, which makes precisely the biggest jump, because it's the biggest amount of energy that you need to get from E0 to E3. Now, what would be the frequency of that photon that it's carrying? This isn't so difficult to work out because we've done this already, and the formula we have used in the photoelectric effect is E is equal to HF. So there's the amount of energy, okay? I can work out the frequency because all I need to do is rearrange this formula and stick in Planck's constant. Planck's constant, as you know, is on the formula sheet. So the next question is, and I didn't write it down, is what is the frequency? Here's the question. You should write it down. What is the frequency of the incoming photon that provides this energy? Okay, so I'm going to use the formula E equals HF. So here's the energy, 20.44 times 10 to the negative 19 is equal to Planck's constant, 6.63 times 10 to the negative 34 times F. 1 mark for doing that, 1 mark for doing this. Now we're going to do a bit of rearranging. 20.44 times 10 to the negative 19 divided by 6.63 times 10 to the negative 34. You can be doing this, or you can just wait for me to do it. So we're going to do 20.44 times 10 to the negative 19 divided by 6.63 times 10 to the negative 34 equals, and that's F. having rearranged the formula, and that is equal to 3.08 times 10 to the power of 15 hertz. That would be the frequency of the light photon that's coming in. Now, I say light in the loosest sense. It could actually be visible light. Depending on the frequency and the wavelength, it could actually be invisible light. It might be below red, it could be infrared and below, in which case you wouldn't see it, but you'd still be able to detect it with the right type of detector. It could be that this is higher than violet, ultraviolet, so you wouldn't be able to see it. But it's so we're using light loosely, not just to include Roy-Gebiv, but actually other bits of the electromagnetic spectrum. So the photon would have to have that that frequency. Now, what would be the wavelength? So next bit. Now I've run out of, I've forgotten my letters now. So I had how many transitions? A, how much energy? B, that must have been C. Sorry if I'm getting this wrong, but D is what would be the wavelength of this photon that's incoming. Okay, so we just need to do V equals F lambda, and it's all the photons in the electromagnetic spectrum travel at the same speed. 3 times 10 to the power of 8 is equal to that answer, 3.08 times 10 to the power of 15 multiplied by lambda. Lambda, therefore, is equal to 3.3 times 10 to the power of 8 over 3.08 times 10 to the power of 15. Similar numbers, don't get caught up there. So I've got 3 times 10 to the power of 8 divided by 3.08 times 10 to the power of 15 equals 9.74 times 10 to the negative 8 meters. Okay. That is the same as 97.4 times 10 to the negative 9, which would make 97.4 nanometers. Doesn't have to ask you for that, but I could then look up in the data table to see if I could find some frequencies that would match with that. That's a very, very small frequency. Sorry, a very, very small wavelength. Now I'm going to keep these numbers. This is the energy from E0 to E3. E0 to E3 is that much. The frequency is 3.08 times 10 to the power of 15. And the wavelength is 9.74 times 10 to the negative 8 meters. And I'm going to keep those because I'm going to refer back to those in a bit. Okay, and I've got to do my running out here. So that was D. So I'm now going to do E, which is what is the smallest amount of energy needed to be absorbed in a transition. So I'm going to go to my diagram and I'm going to have a look at what's the smallest. What's the smallest? And because we've done this and we've tried to do it as a scale diagram, the smallest is this one, and it's E2 to E3, and we can find out how much energy it is by taking those two away from each other. So E2 to E3, E2 to E3 is what's the energy needed? 2.42. Take away 1.36. And all multiplied by 10 to the negative 19 joules. And I'm going to do that on my calculator. 2.42 minus 1.36 equals, and that is equal to 1.06 times 10 to the negative 19 joules. Okay, compared to the biggest transition before, which was this one, this 20.44 times 10 to the negative 19. I'm going to need these numbers again in a minute. Okay, I'm going to repeat myself. F. I'm going to work out what is the frequency of a photon carrying this amount of energy. So I can do this again by using E equals HF, and I've got E 1.06 times 10 to the negative 19 equals 6.63 times 10 to the negative 34 multiplied by F. So F is equal to 1.06 times 10 to the negative 19 divided by 6.63 times 10 to the negative 34. And into my calculator is going to go that 1.06 times 10 to the negative 19 divided by 6.63 times 10 to the negative 34 equals, and that is 1.598. I'm going to leave it as around, it's 1.5987. Let's do 1.599 times 10 to the power of 14 hertz. I'm going to keep a figure here. All right. Before, when I did this, I had 4 figures, 4 significant figures. Here I'm going to keep 4 significant figures as well. Lastly, G, I'm going to write that down on here for E2 to E3, so I want to come back to it, and it's 1.599 times the energy first, 1.06 times 10 to the negative 19 joules, and the frequency is 1.599 times 10 to the power of 14. And I'm now going to do the wavelength. I want to keep that number, so I'm going to use it again to work out the wavelength using V equals F lambda. So that was part F. This is part G. What is the wavelength of this photon? I'm going to use V equals F lambda. 3 times 10 to the power of 8 equals 1.599 times 10 to the power of 14 times lambda. So lambda is equal to 3 times 10 to the power of 8 divided by 1.599 times 10 to the power of 14. I shall work that out. 3 times 10 to the power of 8 divided by 1.599 times 10 to the 14 equals, and that is equal to 1.88 times 10 to the negative 6 meters. Okay, I'm going to write that on my sheet. 1.88 times 10 to the negative 6. Right. Okay, I'm now going to do a comparison thing between all the answers to those questions, which you'll be able to see on your piece of paper. Now, energy. I know that the largest amount of energy is 20.44 times 10 to the negative 19 joules, and the smallest is 1.06 times 10 to the negative 19 joules. Just disappearing in the dark over there. I've got my frequency, and that was E0 to E3, by the way, E0 to E3, and the other one was E2 to E3. Frequencies. I've got 3.08 times 10 to the power of 15, and I've got wavelength. That's hertz, and the wavelength is 9.74 times 10 to the negative 8, and the frequency for the smallest step is 1.599 times 10 to the power 14 hertz, and the wavelength is 1.88 times 10 to the negative 6. Right, now I'm now going to compare these. Okay. The largest energy gives the highest frequency. The largest amount of energy gives the highest frequency. And to use the proper word, that is bigger. This could be the biggest frequency, but I'm going to say it's the highest frequency. Because anything times 10 to the power of 15 is higher than, bigger than 10 to the power of 14. The largest amount of energy gives the highest frequency. And vice versa. The smallest amount of energy gives the smallest frequency. Let's just write that there. Largest amount of energy and smallest, in comparison, I'm using a different color, gives the lowest frequency. Okay. And why is that? Because E equals HF, which means that E is proportional to F, or F is proportional to E. So the bigger E is, the bigger F is. Okay, and vice versa. Let's have a look at the wavelength. The largest amount of energy gives the. Now let's compare the wavelengths. That's meters, and that's meters. Right. Higher the frequency, larger the energy, the smaller the wavelength. This wavelength, 10 to the negative 8, is much smaller than 10 to the negative 6. So the largest amount of energy gives the smallest wavelength. And vice versa. So what does that mean? The smallest amount of energy gives the largest wavelength. Now, why is that? Well, we've got E equals HF, and we did this before in the photoelectric effect. E is equal to HF, and V is equal to F lambda. Okay, so I can rewrite that as F equals V over lambda, and I can replace the F there with V over lambda. So that's H times V over lambda. And you'll remember in the photoelectric effect, we could actually say that is H times C. I'm just going to take out the V because it's 3 times 10 to the power of 8, and the symbol for speed of light is C. Now, H is a constant, Planck's constant. C is the speed of light, which is a constant. So E is proportional to 1 divided by the wavelength, which is an inverse relationship because the lambda's on the bottom, it's inverted. So that's an inverse relationship. So as E gets bigger, the wavelength, you can work it out yourself. E's large gives a very small wavelength. Okay, if this is big, this becomes very small, divided into 1 to match it up. Okay, so you would be expected in tests and exams to identify, you might have to do this, you can remember this is like a summary. You would have to remember, I don't have to do all the sums. The largest amount of energy gives the highest frequency, the smallest amount of energy gives the lowest frequency, and you will need to remember that. You would also be expected at any stage not to do necessarily all of these 6 calculations, but you would be expected to find just one of the frequencies, for instance, or one of the wavelengths. Right, so I think that's about it. I'm just going to take a second. This was actually, or similar, was actually an exam question. I can't remember which year it is, but I got it out of the Davy document. And it's pretty similar. It's not quite, this last bit isn't the same, but the it gives you the idea. I got the energy levels from this, and I'm just going to tell you which year it was. So you can have a look and see what a typical exam question is. On the table, you want to look down the left-hand side for spectra, and this is question 6 in 2017. Question 6 in 2017. It's not, this isn't what I've done. It isn't anything like the question, but all I did was I took the levels here from that question, and then I made up my own exam question afterwards, so you could see how all the comparisons, big energy, high frequency, small wavelength, small energy, low frequency, long wavelength. Okay, and that's it for now. I'm going to stop there once again, and that's our second lesson on spectra.